Welcome to the Deep Dive. Today, we're plunging into something that's, well, not just changing things, it's really reshaping our entire world. We're talking about artificial intelligence and specifically the absolute core of its power, pattern recognition. I mean, just think about it. AI's incredible ability to spot patterns, classify things, act on data at a speed and scale we just can't match. That's the engine behind everything it does so quickly.
Exactly. And our mission here, for this deep dive is to really unpack how AI actually does that, how it identifies patterns, interprets them, and then what are the huge system-wide effects it's having across everything. Plus, the really crucial ethical side of things that comes with technology, this powerful. It's not just what AI can do, but how it sort of thinks and what that really means for all of us.
Okay, and to help us navigate all this, we've drawn heavily from a major report, The Pattern Recognition Revolution, an AI scientific examination of a new human epoch. And we've also got some fascinating bits from A Theory of Everything and Explainable AI, XAI. XAI. So yeah, expect some surprising stuff and hopefully a really clear picture by the end. Right, let's kick things off with the basics. We all kind of feel what a pattern is, don't we? It's like order in the noise, the signal. But how does an AI, a machine, define something that feels so intuitive to us, yet is actually, well, deeply complex?
That's the critical starting point. Because for an AI, that abstract idea gets translated into something very concrete, very mathematical. Think about any data, an image, sound, whatever. The AI first breaks it down into measurable properties. We call these features. A pattern, then, is basically represented as a list of these feature values, a feature vector. So imagine a simple ball. We could describe it by its weight and diameter. Maybe it's 25 units weight, 1 unit diameter. That's 25, 1. But you can add more, right? Color, texture, bounce. Each one is a new dimension. So the AI sees each specific ball as this unique point, this sort of fingerprint in a high-dimensional space. Makes spotting similarities much easier. And importantly, this is very different from simple pattern matching. Like, using Ctrl plus F to find an exact word, that's matching. AI pattern recognition is probabilistic. It's about finding the most likely match, dealing with all the messiness of the real world. Take recognizing cats. And AI doesn't have just one perfect cat template. Instead, it learns a statistical idea of catness. That lets it identify all sorts of cats. Different breeds, colors, maybe partly hidden because it's learned the underlying statistical pattern, not just a rigid template. This ability to generalize, to apply what it learned to new things it hasn't seen before. And that's the real core of it.
That idea of catness is really helpful. Okay, so the AI understands patterns mathematically. But how do we actually teach the machines to see them? How does this philosophical approach to knowledge discovery, as the report puts it, actually work in practice?
Well, there are really three main ways, three main learning paradigms. Unsupervised, and reinforcement learning. Supervised learning is definitely the most common one you hear about. Basically, the AI learns from examples that are already labeled. Think about building a spam filter. You feed the AI thousands of emails, and each one is clearly marked spam or not spam. The AI's job is then to figure out the connections, the statistical links between the input features, words used, sender, etc., and that correct label. It keeps tweaking its internal settings, its parameters, to get better at matching the input to the right output label. The whole point is for it to then generalize this to correctly classify new emails it's never encountered. It's what we call a confirmatory approach. We give it the answers, it learns to confirm them.
Okay, so that's learning with the answers provided. How does unsupervised learning differ? That sounds like the opposite.
It is, quite sharply. With unsupervised learning, the data is unlabeled. No right answers given. Here, the AI's task is more like exploration. It has to find structures, clusters, or any kind of regularities within the data itself. A classic example is customer segmentation in marketing. An algorithm looks at purchase histories, maybe website clicks, and identifies distinct groups, maybe high-spending weekend shoppers or bargain hunters, without anyone telling it those categories exist beforehand. It's exploratory. Fantastic for finding hidden patterns we didn't even know to look for in big, messy data sets.
Interesting. So one confirms known patterns, the other explores for unknown ones. What about the third type, reinforcement learning?
Right, reinforcement learning. The simplest way to think about it is learning by doing. It's kind of modeled on how we learn through trial and error based on behavioral psychology. You have an agent, that's the AI operating in an environment, maybe a game or a simulation. The agent takes actions and then it gets feedback. Rewards for good actions, penalties for bad ones. Its goal is to figure out a strategy, a policy, that gets it the most cumulative reward over time. Think about an AI learning chess. It isn't fed rules like control the center. No, it just plays millions and millions of games. It gets a reward for winning, a penalty for losing. Through all that trial and error, it eventually discovers incredibly complex winning strategies just by trying to maximize that reward signal.
That's a great breakdown. So if I were trying to quickly explain this to someone, could I say, supervised needs the answers, unsupervised finds hidden groups, and reinforcement learns from rewards and mistakes?
Absolutely. That's a perfect nutshell summary.
Okay, so regardless of how it learns, supervised, unsupervised, reinforcement, the sources say there's a kind of standard process, right? A pipeline that all these systems follow, like an assembly line taking raw data and turning it into something useful.
It's exactly right. It's typically a 5-stage process. Stage 1, data acquisition and pre-processing. First, you've got to get the data, text, images, sensor readings, whatever. But raw data is almost always messy. It might have missing bits, errors, noise. So this stage is all about cleaning it up, handling those missing values, maybe chopping it into usable segments. And the absolute golden rule here is better data in, better model out. Garbage in, garbage out is very real in AI. Stage 2, feature extraction and engineering. Now, before deep learning really took off, this was often the hardest part, almost an art form. You had to figure out how to transform that messy raw data into a neat set of informative features, things the algorithm could actually work with. For an image, maybe you'd manually extract edges or textures or color histograms. For text, maybe word counts. The goal was to reduce the complexity, but keep the vital information, separate the signal from the noise, basically.
Okay, hold on. You said before deep learning, so this demanding feature engineering, that was the big bottleneck, and deep learning changed that. How?
Yes, precisely. That's the absolute core innovation of deep learning. It automates feature extraction. Instead of humans trying to guess the best features, deep learning models learn them automatically, directly from the data. They have these layers, right? Hierarchical layers. The first few layers might learn really simple things, like edges or corners in an image. Then the next layers combine those simple features to learn more complex things, shapes, parts of objects. And layers deeper still might combine those to recognize whole objects, like faces or cars. This ability to learn the feature hierarchy itself, without us telling it what to look for, is why deep learning is so incredibly powerful, especially for complex stuff like images or sound. It cracked the bottleneck. Okay, so after features are handled, either manually or automatically, we get to stage 3, model selection and training. Here you choose the right kind of machine learning model for your specific task, classification, clustering, prediction. Then you train it. You feed it a big chunk of your data, the training set, maybe 80% of what you have. And the algorithm iteratively adjusts its internal knobs, its parameters, trying to minimize the difference between its predictions and the actual outcomes in the training data. It's learning the patterns. Then stage 4, classification or decision-making. This is when you actually use the trained model. You give it new data it's never seen before, and it applies the patterns it learned during training to make a prediction, classify something, or group it. This is where you get the actionable insight. And finally, crucial step, stage 5, evaluation. You can't just trust that it worked on the training data. You need to test it rigorously on a completely separate chunk of data, the test set, that it never saw during training. It tells you how well it generalizes to new situations. We use metrics like accuracy, precision, recall, and we watch out for overfitting, where the model memorized the training data perfectly but can't handle anything new. Validation is key.
You know, listening to all that, this trade-off really starts to stand out. The most powerful models, like deep learning, seem to be the hardest to understand internally. You get amazing results, but how it got there, it's often a mystery. It's like this impenetrable black box. And that tension, performance versus transparency, that's really what sparked the whole field of explainable AI, XAI, isn't it?
It's absolutely central. And, before deep learning became so dominant, we relied more on what we now call classical machine learning algorithms. Many are still incredibly useful, and a key advantage is they're often much more interpretable. Take decision trees. They build this flowchart-like structure. They learn simple if-then-else rules directly from the data. So if you want to know why it made a certain prediction, you can just follow the path down the tree. Very transparent, very interpretable. Or support vector machines, SVMs. The idea here is to find the best possible dividing line, or hyperplane, to separate different classes of data points. And for data that's all mixed up and can't be separated by a straight line, they use something called the kernel trick. It's clever. It sort of maps the data into a higher dimensional space where hopefully a simple separation becomes possible, like unfolding a complex origami shape to see the pattern clearly. Then you have simpler things like naive Bayes. These are probabilistic classifiers. They make a naive assumption about features being independent, but they work surprisingly well, especially for text classification, like spam filters. Quick and efficient. And in the unsupervised world, k-means clustering is a workhorse. You tell it how many clusters k you want to find,
And it iteratively groups the data points around cluster centers or centroids, really common for market segmentation.
Okay, so those are the more traditional, often more interpretable methods. But the big leap, the one driving so much today, came with something more complex, right? Where did things really take off?
Right. The huge leap forward came with artificial neural networks, ANNs. They're the foundation of deep learning. They're inspired, loosely, by the structure of the human brain, with interconnected layers of nodes or neurons. You've got an input layer for the data, then one or more hidden layers where the computation happens, and finally an output layer, giving the result. And deep learning. That just means ANNs with lots of hidden layers, sometimes hundreds, even thousands. This depth allows the network to learn those hierarchical representations we talked about, edges to shapes to objects. How do they learn? Well, you show them lots of data. They make a prediction. You compare it to the real answer, calculate the error. Then, using calculus, specifically backpropagation and gradient descent, that error signal is sent backward through the network. And it tells the network how to make tiny adjustments to the connections, the millions of weights between neurons, to reduce the error next time. It's iterative optimization. But the real power wasn't just ANNs in general. It was unlocked by specialized architectures designed for specific types of patterns. For visual patterns, images, video convolutional neural networks, or CNNs, are king. Their design is inspired by how the visual cortex in animals processes information. They use special convolutional layers. Think of these as having small, learnable filters that slide across the image, looking for specific features like edges or textures. The output is a feature map, showing where those features were found. A really smart trick is weight sharing. The same filter is used across the whole image. This makes them efficient and helps them recognize an object no matter where it appears, something called translation invariance. Then they often have pooling layers that simplify the information, making the network more robust. Stack these layers up, and you get that hierarchical feature learning from simple lines to complex objects.
Okay, so CNNs for images. What about data where the order matters, like language or time series?
For that, we have recurrent neural networks, or RNNs. They're built specifically for sequential data text, speech, stock prices, things where the sequence is crucial. Unlike standard networks where information just flows forward, RNNs have loops. This allows information to persist, to be carried along the sequence. They have this thing called a hidden state, which basically acts like memory. At each step in the sequence, the RNN looks at the current input and the hidden state from the previous step. This lets it remember context. So if it sees apple earlier in a sentence, it might use that memory later to correctly predict red or computer. Now, basic RNNs had a problem remembering things over long sequences, the vanishing gradient problem. Signals from far back tended to fade out during training. So more advanced versions were developed, mainly LSTMs, long short-term memory, and GRUs, gated recurrent units. They have special gates inside them that control the flow of information, learning what to remember, what to forget, and what to output. This makes them much better at handling long-range dependencies, which is why they're so good for machine translation or speech recognition.
Wow, okay, so distilling that huge amount of information, and we've got the classic, often interpretable algorithms like decision trees and SVMs, then the deep learning giants, CNNs mastering vision by learning features layer by layer, and RNNs handling sequences using their built-in memory, especially LSTMs and GRUs. And these deep learning models, while incredibly powerful, often bring us back to that black box issue we mentioned earlier.
Exactly. That's the heart of the challenge. The better these models perform, often the harder they are to understand internally. And that black box problem isn't just theoretical, it has real-world consequences. A huge one is the erosion of trust and accountability. Think about it. If an AI suggests a medical diagnosis or denies someone a loan, how can a doctor or a loan officer trust that decision if they have no idea why the AI made it? And if something goes wrong, who's accountable? It's hard to say when the reasoning is opaque. It also makes debugging and improvement incredibly difficult. If a self-driving car makes a mistake and you can't see inside the model's thinking, how do you figure out what went wrong and fix it? And critically, black boxes can easily hide dangerous biases. Sometimes a model gets things right, but for completely the wrong reasons. There was that famous example of an early COVID-19 detection model using X-rays. It learned to associate the severity of the case with things like the position of text markers on the scan, not the actual lung pathology. These kinds of spurious correlations mean a model might look good in testing but fail badly and unfairly in the real world, often amplifying existing societal biases. And lastly, there are growing regulatory hurdles. Things like the EU's GDPR mention a right to explanation. Individuals impacted by automated decisions have a right to know why. Opaque models just can't deliver that.
Right, these are serious roadblocks. So How do we actually get inside the black box? This is where explainable AI, XAI, really comes into play, right? To try and shine a light inside.
Precisely. And XAI makes some important distinctions first. There's interpretability. That's a property of the model itself. How easy is it for a human to understand its workings? A small decision tree is highly interpretable. Then there's explainability. That's the ability to generate an explanation for why a model made a particular decision. Especially for models that aren't inherently interpretable. It's often done after the fact, post hoc. So we talk about white box models, ones that are intrinsically interpretable, like linear regression or decision trees. You can see the logic. And black box models, the complex ones, like deep neural networks, where the internal logic is hidden. XAI mostly focuses on explaining these. We also think about the scope. Do we want a global explanation, understanding the model's overall behavior, like which features are generally most important? Or do we need a local explanation, understanding one specific prediction? Why did the AI approve this loan application or flag this image? Local explanations are often crucial for building trust in individual decisions.
Okay, so if the model itself is a black box, how do these XAI techniques actually generate an explanation? It sounds like they need a way to probe the model without actually cracking it open.
That's a good way to put it. And yes, some of the most powerful techniques are model agnostic. They treat the AI as a black box and work by observing its inputs and outputs. Two really prominent ones are LIME and SHAP. Let's start with LIME, local interpretable model agnostic explanations. The core idea is pretty intuitive. Even if a complex model's overall behavior is confusing, right around a single specific data point, its behavior might be simple enough to approximate with an easier interpretable model like linear regression. So how does it work? You take the instance you want to explain, then you create a bunch of slightly changed versions of it, like removing some words from a sentence or blacking out parts of an image. These are perturbed samples. You feed all these perturbed samples to your original black box model and get its predictions for each one. Then you weight these samples based on how similar they are to your original instance. Finally, you train a simple interpretable model like linear regression just on this local neighborhood of perturbed samples and their predictions. The explanation comes from that simple model. For linear regression, the feature weights tell you which words or image patches push the prediction one way or the other for that specific instance. It gives you a local peek inside.
That's clever. So it builds a simple map of the immediate vicinity. What about SHP? You mentioned that's another big one.
Right, Shapley additive explanations. This one comes from a different place. Cooperative game theory, specifically Shapley values. Think of the prediction process as a game. The players are the different feature values of your input, like age, income, purchase history. The payout is the model's final prediction. SAP calculates the contribution of each player, each feature to the final payout or prediction. It does this by considering all possible combinations of features and figuring out the average impact each feature has when added to a coalition. It has some nice theoretical properties, like ensuring the contributions add up correctly, local accuracy, and being consistent. A big advantage of SAP is that it can provide both local explanations for single predictions, often shown as force plots, and global explanations, by aggregating the SAP values across many predictions to see which features are most important overall, like in summary plots. It's usually more computationally intensive than LIME, but its strong theoretical grounding makes the explanations often feel more robust and reliable.
Okay, so summarizing those. LIME is great for quick, intuitive local explanations by approximating locally. SHT is more computationally heavy, but offers a theoretically sound way, based on game theory, to assign contribution values to each feature, giving both local and global views. Both are vital tools for opening up that black box. Let's zoom out again. This ability for AI to recognize patterns isn't just a technical detail. The sources frame it as a general-purpose technology like steam power or electricity. It's fundamentally changing how everything works, isn't it? And the report talks about this profound duality between empowerment and control.
That duality is everywhere you look, and the scale is immense. Economically, AI's pattern recognition is projected to add something like $15.7 trillion to the global economy by 2030. In finance, you have algorithms dominating trading, reacting to news and sentiment in microseconds. Fraud detection systems use AI to spot anomalies in billions of transactions, saving massive amounts of money. For supply chains, AI optimizes everything from demand forecasting using sales data, weather, even social trends, to calculating the most efficient delivery routes in real time. It's also becoming a huge tool for environmental stewardship. For climate change, AI helps process vast amounts of satellite data to improve climate models and build better early warning systems for extreme weather. That's critical for adaptation. In conservation, AI analyzes camera trap images or drone footage to track endangered species or detect illegal logging. Acoustic monitoring can identify animals by their calls, even helping in anti-poaching efforts. And for pollution, AI enables real-time air and water quality monitoring and prediction. In public safety and justice, it's a mixed bag. You have predictive policing using historical data to identify potential crime hotspots for patrols used in cities like Chicago. Then there are technologies like Zero Eyes, using AI with cameras to try to detect firearms in public places, alerting authorities within seconds. Politics and information is another area where it cuts both ways. Campaigns use AI for micro-targeting, analyzing voter data to create highly personalized messages, like the Cambridge Analytica situation highlighted. On the flip side, AI, especially natural language processing, is used to detect and flag misinformation online. But the same AI tools, especially generative AI, make it incredibly easy and cheap to create convincing deepfakes to spread disinformation. It's an ongoing battle. Healthcare is seeing a massive transformation. AI, especially CNNs, is getting incredibly good at advanced diagnostics from medical images, X-rays, MRIs, sometimes spotting things human radiologists might miss. It's driving personalized medicine, analyzing genetic data, lifestyle factors to tailor treatments, and it's dramatically speeding up drug discovery by simulating how millions of potential compounds might work.
It really touches every area. What about education and industry?
Absolutely. In education, AI is enabling personalized learning paths, adapting to individual student needs in real time. You have intelligent tutoring systems offering support. And AI can augment teachers by handling routine tasks like grading, freeing them up for more human interaction. Though there are concerns about potential oversurveillance too. In industry and commerce, it's the engine of Industry 4.0. Manufacturing uses AI for predictive maintenance, analyzing sensor data to fix machines before they break. Generative design uses AI to explore thousands of potential product designs. And AI-powered quality control uses computer vision for inspection. Retail relies heavily on recommendation engines, think Amazon or Netflix, and uses AI for dynamic pricing and demand forecasting. The energy sector uses AI to optimize smart grids, integrate renewables by predicting wind solar output, and manage energy consumption in buildings. And even in our social and personal lives, AI is analyzing patterns. It looks at social media, news trends to understand cultural shifts. But we need to be aware AI models aren't neutral. They can reflect and reinforce cultural biases from their training data. For instance, language models might show different personalities depending on the language used. It can even analyze communication patterns for insights into relationships or gender dynamics. But again, there's a huge risk of AI learning and amplifying existing gender biases, associating doctor with men, nurse with women, for example. Though AI can also be used to surface and measure these biases.
It's striking how AI acts almost like a mirror, or maybe an amplifier, reflecting and sometimes magnifying our own societal patterns, including the flaws. We've touched on risks like bias, but what are the biggest dangers we need to grapple with as this technology becomes more embedded?
That's the critical question. And a responsible approach demands we confront these risks head-on. Algorithmic bias is perhaps the most discussed, because AI learns from data, and our historical data is full of societal biases, racial, gender, socioeconomic combined. The AI models learn and perpetuate them. We see it in facial recognition, having higher error rates for people of color and women. We see it in hiring tools, favoring candidates similar to past hires, often white men. We see it in predictive policing, focusing more on minority neighborhoods. It's not intentional malice by the AI. It's learning the patterns, flaws and all, from the data we feed it. Then there's data privacy. AI needs massive amounts of data, which creates huge challenges. There's non-consensual data collection, scraping data from the web. There's data repurposing data collected for one thing being used for another without consent. And even with regulations like GDPR giving a right to be forgotten, actually erasing someone's data influence from a huge complex model is technically very, very difficult. And beyond biases and privacy, there's the potential for misuse. Mass surveillance by authoritarian regimes, combining AI with cameras to monitor populations. Workforce disruption is a major concern. AI will automate many jobs, especially routine ones. While new jobs might emerge, there's a real risk of increasing economic inequality if the benefits aren't shared widely. We need plans for reskilling and social safety nets. And then there are the security implications, ethical debates around lethal autonomous weapons, and the use of AI in sophisticated cyber attacks.
Okay, so facing these significant risks, bias, privacy, misuse, economic disruption, what's being done, how do we build those guardrails you mentioned?
There's a growing global effort, thankfully. It starts with establishing principles and frameworks. The OECD AI principles were a landmark, the first intergovernmental standard for trustworthy AI. They focus on things like inclusive growth, human-centered values, fairness, transparency, robustness, safety, and accountability. Translating those principles into practice involves integrating ethical guidelines into the entire AI development process. Key elements include fairness and bias mitigation. That means actively working to get diverse, representative training data, using tools to detect bias in models, and applying techniques to reduce that bias. It also means a strong commitment to transparency in the use of XAI, using inherently interpretable models when possible, and applying tools like LIME and SHAP to explain black box models, especially when the stakes are high. Another vital piece is human-in-the-loop oversight. For really critical decisions, medical, legal, financial, the AI should ideally be a tool supporting a human expert, not making the final call alone. This keeps humans accountable. And finally, there's a lot of research into privacy-preserving machine learning, PPML. Techniques like federated learning, training models on decentralized data without moving it, differential privacy, adding noise to obscure individuals, and homomorphic encryption, computing on encrypted data, aim to let us train powerful models without compromising raw data privacy.
This has been an absolutely fascinating journey into the core of AI. It really drives home that mastering computational pattern recognition isn't just another technological step. It feels like a genuine watershed moment, changing how we relate to information, to our environment, even to ourselves.
It really is. And perhaps the most profound insight from the sources is that the ultimate potential here isn't about AI replacing us, it's about augmenting human intelligence. Think about it. By handling the heavy lifting of finding patterns in vast amounts of data, AI can free up human minds to focus on what we do best. Things like creativity, critical thinking, long-term strategic judgment, emotional intelligence, ethical reasoning. The sources paint pictures like the AI-assisted radiologist who can spend more time actually talking with patients, understanding their context, or the AI-supported teacher who has more time for individual mentoring. The scientists using AI to sift the data, freeing them up to form bolder hypotheses. It's about a partnership.
But as you've made clear, that positive future isn't automatic. It depends entirely on the choices we make now. It depends on building effective governance, ensuring human values guide the algorithms, and being constantly vigilant about the risks. The goal has to be ensuring these incredibly powerful tools serve our best intentions as humans. Thank you so much for unpacking all of that. And thank you, our listeners, for joining us on this deep dive. We really encourage you to keep exploring this incredibly important topic.
This is DigitView.